So, good morning everyone. Today we are going to explain a bit about the concept of configuration space. So, in order to do this, we'll have a series of lectures discussing, first of all, the base manifold of configuration space, so configuration space itself, and then we will move on to explain how we define its tangent bundle, its cotangent bundle, and we will do all this focusing on the physical perspective. So we will try to keep a reasonable physical insights. We will use parameters instead of general coordinates, and we will use these parameters to identify points on the manifold. So we won't actually deal with abstract manifold points or abstract manifold entities. So hopefully this will prove useful for you to understand the basic notion of configuration space, and anytime later on you can actually learn the differential geometry that's behind it. Okay, so first of all, let's introduce the subject by recalling Newtonian mechanics. So when we do classical mechanics, we normally think of three-dimensional space and particles moving on arbitrary trajectories in this three-dimensional space. So this is indeed a very general picture, and the classical laws of motion, so Newton's law, i.e. the concept of force, the concept of inertia, and inertial frames, inertial coordinates, Cartesian coordinates, so on and so forth. These provide the natural framework for classical mechanics in the Newtonian formulation. So in that context, what we had was trajectory, particle, right? So we actually had a particle moving in three-dimensional space, and we essentially always identified the particle's position with a position vector that's depending on our parameter, and so essentially we had this coordinates, so say x, y, and z, and of course each of the projections depending on t, so this is essentially x of t, y of t, and z of t. So of course the way this motion was described was with this idea of a trajectory, of a smooth, continuous curve on R3, or three-dimensional Euclidean space. Now, if we want to generalize this notion a little bit, we want to include any sort of restrictions, constraints, and general kind of conditions on the motion of the particles beforehand we actually find the dynamics of the particles. So for instance, we could very well imagine a particle moving on a ball. So for example, if we picture a ball like this, right? So you can imagine a little marble, small ball, moving back and forth. This three-dimensional, right? So it's still the very same description. So we've got three-dimensional space here, but now the particle is restricted to move on the surface. So it cannot go elsewhere. So it's got a restriction already, and the power of Lagrangian and Hamiltonian mechanics, or it's normally referred to as analytic mechanics, is that instead of worrying about the forces, the normal force of this surface, and maybe obviously I need some kind of support here, so maybe a base or something, so that this makes sense. Instead of worrying how this actually works and describing the properties of this material and properties of the contact between the marble and the material, so on and so forth, analytic mechanics, that's precisely what is interesting for understanding the general traits, the general idea of how the dynamics work. So, in this case, for instance, we will say, okay, so the particle has got only 2 degrees of freedom, in the sense that instead of being able to move freely in 3 space, it can only move restricted to this surface in this paraboloid, right? So this is the very idea that's behind the notion of configuration space. And so I will define it formally now, but I want to stress that this is a very, very general sort of notion, and today we will restrict ourselves to systems of point particles in 3-dimensional Euclidean space. And so, of course, the configuration manifold could be, for individual particles, can always be pictured as some sort of subspace or subset of 3-dimensional Euclidean space, right? So we will first discuss the case of one particle, and then we will discuss the case of many particles, which is absolutely equivalent. There's no difference mathematically at all between those. So let's have a first look at our definition of configuration space. So let me first. So we're concerned about describing the motion of particles that are restricted to somehow live on a region of 3-dimensional, on a restricted region of 3-dimensional Euclidean space. And so, first of all, I think it's useful for us to describe a general way, or it's good for us to actually set a good mathematical notion for these kind of things. So what I'm going to do now is to define what is called a parametric manifold, which is indeed a particular case of a general differentiable manifold, but is the kind of notion that we're going to use as our space, our configuration space indeed. So let's see how we could do this. So consider, of course, let's do it, because I'm not sure if I want to do this three-dimensionally or arbitrary dimensions and just have a picture. Alright, let's make it general dimensional. Let's make it general dimensional, and we'll have a picture. Yeah, let's make it so. So, let's consider many dimensions, right? Which in our case is going to be 3 most of the time, well, always, for the one particle case. And we want to consider subsets. So subsets that geometrically have a well-defined dimension. This is the informal way of saying that they are submanifolds, right? So we have curves, well, we have indeed just points, we have curves, we have surfaces, right? And indeed, we have closed curves, we can have closed surfaces, right? So these are the kind of objects that we want to describe in our space. So how do we do this? So essentially, it is important to notice that these objects are characterized by points, and they have a very particular property, and that is we can always find other points that are smoothly connected with them. So this geometric property, right, is what makes it relatively easy to describe mathematically. So let's just give a formal definition, and we will see. So what we're going to do is we define a map from Rn, which is of course of n numbers upstairs into Rn. So say we call this x u1 n. Okay, right. So this is the map that we like, and of course we assume this is smoothly differentiable, continuous, and all the smoothness requirements that we like. Okay, so how does this look like? What does this map actually mean? So imagine that we want to picture map. So let me make a very particular picture of this. For a particular dimension. So say we've got a case where n equals 2, m equals 3. So we have a map of this kind, so that I can draw it. So u1, u2, into usual 3 component vector. Oops. Okay, so how does this look like? Well, we have, and now I would like to introduce some terms that might be useful for our discussion, and that is going to be the generalized coordinate space or parameter space, which is always a subset of R2. So in general, it need not be the whole R2. So we can always make it the whole R2, but in particular examples, it's just useful to consider some subset. There's no real problem in that. So we have R2, and we have actually a subset of R2. Could be a whole R2, there's no problem with that. Okay? Now we have obviously Q1, Q2. And then we have the map phi into our three-dimensional space that I don't want you to regard as a space of triples of numbers, but this picture is a three-dimensional Euclidean space. And here we have something like this. Okay? So I have this surface. Okay? So this is what this map is actually doing. Okay? So obviously for particular cases we could have embeddings. For instance, if you think of this spherical coordinates, you just plug here the angle phi, angle theta, and then you have an embedding that's from, let's make that example. That example is really useful for you to visualize what this actually means. So for the two-sphere, we have a map, let's call it sigma for sphere, maybe. But a map, its kind, so it's a sphere. Two-sphere. You have your parameter or generalized coordinate space, in this case, it's going to be usual phi theta. It's going to give you, let's say you radius 1, really kind of three real numbers, which is sine, So now we are not actually using all the R2, we're actually restricting ourselves to a subset. So you all know very well that in order to cover the whole sphere, we use from 0 to 2 pi and from 0 to pi here, right? Okay, so we use this region, R2. So notice how this R2 is just a space of parameters. It's no geometric kind of space. It's just a set of labels that we will use in three-dimensional space. And now sigma, or sphere map, gives us this nice right? And of course like this. Okay? So of course, you can see in the example that this is our space, and the parametric manifold, or what we call our configuration space, is just this shape, this shell. So it's obviously empty. So we have an arbitrary point here, call it phi theta, gets mapped into a point here. Right? And since this map is smooth and continuous and with all the requirements that we like, if we move around here, we will have a curve that, let's make it longer, right? We'll have a curve that will move around the sphere, but it will always be contained in the sphere, right? Or on the surface. So, okay. So I hope this is a good picture. And I'm actually going to use it for other notions of this particular construction. So this is what is called a parametric manifold, and indeed that's what we are going to define as our configuration space. So in particular, the image of all the points. So for instance, the image of this rectangle in R2 is the whole sphere here, right? So in general, when we do mechanics, we say that the image of all possible parameter values, so all possible Q's, is the configuration manifold. It's the configuration space. So just as a definition that you must bear in mind, conceptually, again, this is not very useful for practical purposes, but conceptually, we have a Q equals the image of, by this map, of the set of all parameters. So I'm going to write it like this. All possible Q's. Which could be all the Rn or just a subset in this case. Okay? So in our example, configuration space would be a sphere. Right. Right, so let me discuss a bit more geometry of these things, of these parametric manifolds. Again, I'm going to use this two-dimensional example because it's the one that I can draw in the blackboard. But hopefully, this will easily generalize to higher dimensions with no trouble. Okay, so consider. Well, remember that we always have this set of curves of straight lines in our parameter space, which are the usual lines of constant parameters, in which all the parameters are remain fixed except for one that varies, right? So these are very natural curves, and indeed. We have Q1, for instance, fixed, and so Q2 could vary for any value inside this set, say, and then we have fixed Q1, then Q2 varies for all possible values, and then similarly, if we have a fixed value of Q2 and Q1 varies, we get that. Of course, we do that for all possible values, and then we get this kind of grid, right? Right. So these are horizontal lines are set of parameters of constant Q2, and vertical lines are a set of parameters with constant Q1. Right. So the good thing about this map is that we have a proper embedding, proper realization of these straight lines in our three-dimensional space, which in our case will be R3, of course. And yes, so these curves here get mapped. So let me get mapped something like this. Of course, you can very well imagine. Right, then like that. Something like that. Okay, so you can see those curves kind of form a coordinate kind of grid in that surface. So this is why these are called generalized coordinates, because they are a way of identifying points on this generally complicated surface. Right. So if we take two different curves, so they go through a specific point, of course. Take this point, for instance. Take this curve. Let's say this one. Take this curve. Say this way. Then take this curve here. This way. Of course, we will see that this gets mapped to the surface, and so this curve will be something like this. Okay. Okay, and then this curve get mapped something like this. Okay, so you see how things in this parameter space, which is non-geometric, it's just a set of labels, actually, due to the smoothness of this map, provide us with very nice curves on this space. So in particular, on the sphere, these curves are very, very intuitive, very recognizable. So for instance, take a curve to this point of constant, say constant theta, like this. Okay. Curve like this. And take a curve constant phi, right? And so, you know, the angles, theta is this vertical angle, and phi is the usual polar angle on the xy plane. So if we move along a line here with a fixed theta parameter, that means that we remain at a fixed height, say, so fixed theta, fixed theta value means fixed z height, right? Because I mean the projection is constant. So, and since we move around here, then it means that from this parameterization, as we see clearly, and we move in a circle with the radius sine theta, right? So that's easy to visualize. This is a curve, this one. Okay, so it's a circle that direction. And of course, so it's a parallel in this geographical language that's a parallel. And a vertical line, so in this case remain phi being fixed, so it's a plane polar angle fixed and varying theta. So indeed we go through a meridian, right? So we go like that. And in this case, that's an interesting thing. In this case, this value up here corresponds to this North Pole, and this value down here corresponds to the South Pole. So actually, we have something like this. Okay, so it starts down here, it's below, and it goes all the way up to the North Pole. But it doesn't go around, so because our parameters are defined like that. Okay? So, but that's alright, because obviously if we take all the possible values of phi, we recover the whole sphere, so we recover the whole space. Okay? So this is the basic geometric idea of what parametrized manifold looks like. Okay? So when we do mechanics and we deal with configuration spaces, this is just the mathematical concept that is behind. So just for you to know, let's find, well, actually, let's have a brief discussion on the tangent space of these things. And in theory, I'm going to use this picture. So we have the basic structure. We just we explained, right? We have this coordinates, these parameters, and we have this embedding, and so it is very natural. Well, we've just seen this, but it's very natural to consider these curves, which can be called coordinate curves or parameter curves or constant parameter curves, and they are naturally given once you move in parameter space. As in this picture, once you move in parameter space, you have a curve in parameter space, you automatically have a curve in general free space, but that is restricted to the surface, to the manifold in this case. Okay? So a very natural thing to ask is, okay, so if I have a curve, a natural geometric object that we need to know about a curve is a tangent, it's a tangent vector of the curve. So the tangent vector of the curve, as you know from Euclidean geometry, is just the derivative of the vector. So in this case, we've got a special sort of curve, because it's a curve that is actually contained in a surface. So the tangent vector will always lie on the tangent space of the surface, the tangent plane of the surface at every single point. And so indeed, if we consider these curves, and say we're dealing with Q1, Q2, as being constant along these curves, so it's natural to say, okay, when you calculate a tangent of a curve, you have to compute the derivative with respect to the parameter. So for instance, in this case, the parameter Q1, sorry, the parameter Q2, sorry, the parameter Q1 is constant and the parameter Q2 is varying. So the tangent to this curve will be the derivative with respect to Q. Oh, I'm sorry. It's really unimportant, but it's just I want to be consistent with my notation. Okay. So this is the derivative with respect to Q2. And I say partial because we have two variables, but I mean, as a one parameter, this is an ordinary derivative. So, and the other one is the partial with respect to Q1, which again, they say it's an ordinary one variable derivative and represents the tangent vector along this line. Okay, so formally speaking, if we label this point as being, you know, a certain value q1, q2, these things are only defined at a specific point. So we have this arrow to be, so let me call it v1, v2. So v1 equals this thing when we consider the point q1, q2, and then v2 equals this thing when we consider the point okay. So at this stage this is really interesting because you say, well, I mean, why do you use this funny notation of partials if this is just the canonical basis of R2, so this is just 1, 0, and this is just 0, 1. Okay, so that's right, that's the case, but when we use this map, we have the same story, but here in three-dimensional space and restricting to the tangent plane of the surface at every single point. That indeed, if the surface is curved, this will vary from point to point. Okay, so in this general space, let me picture it properly. We map this point, which we call q1, q2, because it's completely generic. We have tangent plane. You say, so how do you define this tangent plane? So the tangent plane should be a two-dimensional plane. So a two-dimensional affine submanifold, affine subspace. So it should be spanned by two linearly independent vectors. And so what are these vectors? Well, those vectors are actually the derivatives along these curves, right, as we discussed already. In this context it's absolutely trivial. In this context it becomes non-trivial because we are in a three-dimensional space. So we have this, we have that. Okay, and so that for short, oops, this for short, let me call it Q2, this for short is called Q1. So partial with respect to Q1. Okay? So why does this notation make sense now? Because if you recall from the definition here, x depends on Q1, Q2, and so this curve, right, that curve is actually x depending on, x depending on, so Q2 is fixed, the definition, it's fixed at Q2, trace this line, and then Q1, again, right, and Q1 varies. So Q2 is fixed, Q1 varies, and so x varies. So this is the position x along this curve, and so what is the tangent vector to that curve at a certain point? You know how to calculate this. This is just a curve that depends on one parameter. So what you do, you say, okay, it's the derivative with respect to the parameter, right, at the specific value of the parameter, okay, wherever it is, so Q1, Q2, wherever. Okay, I say yes, that's absolutely right, but you know, when we differentiate with respect to variables and we explicitly mean that just the variable that we're differentiating with respect to is the one that is varying, the rest have remained fixed, then we call this a partial differential, so a partial derivative. And so of course, you know, that this is what you have. So this is a tangent vector. So this is why we simply call it partial Q, just to summarize all this story. And equally for x, which we fix Q1, but Q2 varies. So again, the tangent vector to that, you know how to compute that, you just vary Q2. Yet again, at the specific point we're considering. Okay? So remember, this notation means evaluated at Okay, so don't worry too much about that. Okay, so that means, well, for notation, this is called the tangent space at, so let me call that point x in general. Okay, so it's a point of the 3 space, but in our case, since we are parameterizing this surface with q1, q2, it's just the tangent space at that point of this whole surface that I'm gonna name now, and as I name that, so the image of this, of all possible q's, right? That's q. So tangent space of q at the values at a specific point given by the parameters q1, q2. Okay? So this is the general discussion of parametric surfaces in 3-dimensional space, but again, this is the only one that you can actually picture. Well, you can also picture a 1-dimensional curve, but this is really uninteresting because all the tangent spaces are just lines, straight lines. There's no notion of more geometry than just the curve being with you, and the tangent spaces being straight lines that kind of vary along the line. So this kind of encodes the whole geometry that there might be. And so you see these notions particularize perfectly well to the case of the sphere. So note that this discussion was made at every single point of the surface, but it's absolutely independent of which point we like. And so if we pick another point, we'll have the same exact same discussion, and we pick another point, exact same discussion, another point, right? So we basically construct tangent vectors to coordinate or parameter curves at every single point of Q. So that means that it gives, and it's smooth because this map is smooth, that's basically what it's, and smooth means that all the derivatives are smooth as well. So that means that we have a smooth assignment of tangent vectors corresponding to every parameter. And how do you compute that? Well, just take the tangent to the parameter curve corresponding to that parameter, or the tangent to the other parameter curve, right? So that means that we effectively get vector field associated to each parameter, right? And since those vector fields are just computed with this expression by evaluating at a specific point, the notation is naturally just drop the point that you want to consider. So if you drop this, this has somehow a free argument on the base point in which you compute this, and so this, as an entity, is a vector field. Because it gives you a rule that if you provide a point, or a couple of parameters that identify one point, then it gives you a tangent vector at that point. In this case particularly, it gives you precisely the vector that is tangent to the parameter curve Q1, and this gives you the tangent vector to the parameter curve Q2. Okay, so this, and of course in general, I mean, since this map is usually just assumed to exist, and it's not really important how it does the embedding, how it maps into the space, we simply call these vector fields like this, right? So in the picture, this should be that evaluated at Q1, Q2, and this should be evaluated at Q1, Q2. And of course, these are elements of this space, and they span this vector space, the tangent plane at that point. Okay? But now these are vector fields. These belong to the whole surface, and they provide the tangent at every single line. So you see here you have these vectors, and they translate in tangent vectors to this surface. So let me picture those vector fields here. So those vector fields here are so let me see. Yeah. So they are d by d phi and dy d theta. So these are vector fields that have values equal to the tangent of the parametric curves at every point of the sphere. So the value, so yes, so let's just have a picture of how they look like. So maybe, yes, let me draw a new sphere. It's going to be slightly better. Okay. Yeah. Yes. Okay. A sphere, as you can very well imagine, these lines, the constant theta lines, go from the North Pole, from the South Pole to the North Pole. So here it is. So we have, I'm going to draw so these are actually parametric curves. So phi constant parametric curves, so theta parametric curves, and of course these are those are theta constant parameter curves, so phi parameter curves. And now the vector fields will be just drawing the tangent arrows to these curves at every point. So I'm going to do it for you to see what they look like. Okay. Okay, so those that field of arrows, that whole field of arrows is that vector field. So that's the entity. That's an entity that comprises all these arrows, all this smooth distribution of arrows. And then similarly for the other. And that is that vector field. Okay? So this is a picture of the basic geometry of this sort of mathematical characterization of parametric manifolds. So I hope that this is clear enough, and the next lecture will be the concrete mechanical description of configuration space. Thank you.